undergo, some of which we kind of saw a little bit today. And then we'll talk officially about benzene sort of guys and the ring and all that kind of stuff. So last time in discussion, we were talking about, really, we finished up sort of on cis and trans isomers. And remember that in order to have a cis or trans isomer, it really revolves around the carbon-carbon double bond. And again, this is chapter 11. Yeah, we're still working there. And a couple important things when you isolate that double bond, in order to just be able to have a cis or trans isomer, you do need to make sure that each of the carbons in the double bond have two different groups attached. And again, you also need to make sure that there's also a common group between the two carbons. So in this case, A and B are different on the carbon on the left, B and D are different on the right, and obviously B is the same on opposite carbons. And they are opposites of each other, which means this would be the trans isomer. Remember, cis being basically the same side of the double bond. We also sort of finished up talking about the idea that you do want to make sure that you count up the carbons correctly, especially if they are drawn in sort of the cis or trans orientation. Again, sometimes people focus so much on the center there that they forget all about, what the number of carbons are. So this is, I think, where we left off our last time. And again, what's highlighted here is the longest carbon chain, and it actually is 4 rather than obviously 2. And that means that's why we have our butene, and it is 2-butene where the double bond is located. So we do need to give the location when we got like 4 or more sort of carbons involved. And our location of our groups would be 2 and 3 dichloryl. The chlorine groups are both on the same side, and also so are the methyl groups as well. Same thing here, 1, 2, 3, 4 is our longest carbon chain, which also would be butene, with our 2-butene being where our double bond would be located. And again, at carbon 1, 2, and 3 here, this would be 2, 3 dibromo, actually in this case, 2, 3 dibromo, 2-butene. And this would be the trans, obviously, sort of situation. And same thing here. So you do want to make sure you got that sort of down in terms of the longest carbon chain. Sometimes people miss it. And I think we might have talked about it as well, but just in case, let's just take this first guy's name there, which is cis 2,3-dichloryl. Cis 2,3-dichloryl. And I think it was 2-butene, if I'm not mistaken, there on that. So if you are asked to maybe draw this guy, sometimes it's very much easier just to draw it straight without the cis or the trans part of it. So here we would start with just this part, and you would do your 4 carbons. You would do your double bond at carbon number 2. And then obviously, if this is carbon number 2, I do have a chlorine there, and I do have a chlorine here. And then you could put in your hydrogens. And now what you can do is you could really illustrate what you want to draw. Let's just say we were doing trans or cis on this particular guy here. If we were doing this, we could just draw it straight. And then what you would want to do is really just isolate your double bond if you wanted to show the cis or trans really, and just start with the double bond. And then you could take a group up and up, take the other group down, and thus that would draw obviously our cis location. If you wanted trans, you could do the same thing. Once again, start with a carbon-carbon double bond, draw a Cl up, a Cl down, and obviously a methyl up and a methyl down, and that would be your trans. So sometimes people struggle if they're asked to sort of draw the cis or trans sort of isomer. Sometimes it's easier actually just to draw kind of 2 pictures, one just a regular picture isolate the double bond, then kind of move the groups where you need them, either on the same side or opposite sides of the double bond is sometimes really the easier way to sort of do it. Any questions on that there? For obviously it's the cis. And even with the line structure, you could just start with the double bond and then move it around where you need. And that would be your trans. So a good way, if you're again trying to draw these things to show the cis or trans, is really just to kind of start with that double bond, and then you could just move your groups. And it really could all start with just drawing it straight like I did here. And then again, just you could even circle your groups, and then obviously you could move them whichever way you need to move them to illustrate the cis or the trans part of it. So remember, if you do end up though with a carbon-carbon double bond where you do end up with a same group on one of the carbons, then obviously you cannot have cis or trans because this guy has the same groups. So that eliminates the possibility of cis or trans. Any questions on any of that there? Very good. Yes. Okay. Okay, then we'll pick up with some addition reactions that occur with alkenes. And addition reactions are pretty much like the name implies. And in the case of alkenes, pretty much, as I mentioned before, there's really only one part of the molecule that really changes. And when you're doing an addition reaction, it is the carbon-carbon double bond. That's the most important part. Absolutely everything else stays the same in these type of reactions. And really what always happens in these reactions is basically you go from a double bond to a single bond. So you go from a double bond to a single bond. And in these addition reactions, basically what you end up doing is add one thing to one carbon and something to the other carbon. So that is always what happens here. Unlike the substitution reaction that we talked about with alkanes, in an addition reaction, we're actually putting two things on. And this is always what happens. And this is the only part you should remember is I'm just going to take my double bond and make it a single bond. And then I'm going to put one thing on one carbon and one thing on the other carbon. And again, the rest of the molecule will look the same. So for example, if you did and I'll just draw the hydrogens here. There's a couple of hydrogens that are there. And if we added H2 to this, this is what is known as an addition reaction. We're basically adding two hydrogens. So when I look at this thing, the only thing I should really be concerned with is pretty much the double bond that is there. And I'm going to pretty much do exactly what I just said. I'm going to draw exactly the way it looks. And the only thing I'm going to do is just make the double bond into a single bond. So if I do that, and again, without really even thinking, I'm just going to copy exactly what is there, making my double bond into a single bond. I'm going to keep my H's like I had before. The reason, again, that we need to make really the double bond into a single bond is if I wanted to add something to the guy on the left there, and I just put like a hydrogen here, is that okay? I just put the hydrogen right there. It is not, because carbon ends up with like 5 bonds, which is too many bonds. So in these addition reactions, basically we need to make room for those guys that are coming in to be able to bond in and not have more than 4 bonds. So that is really the reason why we get rid of the double bond and make it a single bond, so that we now have obviously the room to do that. Now, in this particular case, you can't really screw up here because frankly, there's only a hydrogen that you're adding. So one hydrogen goes to one carbon and the other hydrogen goes to the other carbon. And no, because that is what I'm putting right here. Yep, that's the H2 that goes on right there. Yep. So we go in this case, this is actually what is known as a hydration reaction. Hydration because we added hydrogen. This is also what is sometimes referred to as a hydrogenation reaction, right? When you see foods that are partially hydrogenated, that is basically what it is. They take away some of the double bonds by adding hydrogen to it. It changes the characteristic of things that makes it a little bit more solid. So you take oil and you partially hydrogenate it, you get like margarine and stuff like that. And so that's what is happening in this situation. So we go really in this case from an alkene double bond to an alkane in this particular reaction as a result of adding those hydrogen in. So in this case, everything comes in, nothing goes out, like in the substitution reaction that we talked about with alkanes, where the hydrogen goes out, everybody's coming in. And it's always the exact same method here. Double bond becomes single bond, and each carbon gets one thing that goes in. Any questions on that? So hydrogenation and a hydration reaction. Hydration is basically adding water, and it works the same way. There's really two types of addition reactions that occur. Some are what are referred to as being symmetrical additions. And that is when you take like an alkene and you add something like H2, maybe Cl2, maybe Br2. And these are what are known as symmetrical additions because basically you're adding two of the same things, right? You're adding two hydrogens, you're adding two Brs, you're adding two Cls. Again, you can't really screw it up because frankly, you just need to put one on each of them. So it doesn't really matter where the one hydrogen goes because really another hydrogen is going to the other carbon. It's the exact same element in those cases. You will sometimes see catalysts written up on top like platinum, nickel, palladium, used as a catalyst for this reaction. They don't do anything other than speed up the reaction that occurs. Now, a hydration reaction is what is sometimes referred to as an unsymmetrical addition. And that is when you add something like water, which is added as H and OH. You could add something like HCl, HBr. It's basically H and something else being added in here. It works exactly the same way, except that you actually end up with a couple of options as in terms of what you get as a product. And that's because you're not adding two of the same things. You're adding H and OH or H and Br. You have a couple of options as to what you get. There's actually a rule that you should follow in terms of how this stuff goes on. You will also, again, sometimes see a catalyst written on top, which is H+, which means it's an acid being used as a catalyst. So let's talk about some examples of these guys here. Let's take a look first off at symmetrical additions. So let's just say we had and we'll just say for the fun of it, let's just add some chlorine, some Cl2. I'll just put, that's basically two Cls. Yeah. All right. So why don't you give it a try and see what you think the result should be. Again, it should be exactly what I just said. Basically, double bond should become a single bond and put on each of those guys. So see what you come up with. A double bonded guy or alkene, and we're adding something, especially something that are two of the same things, basically, is definitely going to be this addition reaction, which means your only concern here should be right there. And pretty much you could start drawing on the right-hand side because you pretty much have the entire structure right there on the left. And again, what you should know is our double bond will become our single bond. And that's really the only change that you need to make. And if you do that literally right away, you could just start redrawing it exactly the way it looks. I'm just going to do it underneath. So we're just going to go exactly the way it looks. We're going to now make that a single bond. Again, the purpose of that is to make room for everybody that's coming in. We're going to just copy exactly what is there. And pretty much you have 98% of the molecule drawn for you already. At this point, we can now pretty much add a chlorine to each of the carbons that was in the double bond originally. In this case, because this is symmetrical, you can't screw it up. You just need to put the chlorines on those two carbons. Again, each one gets one, and then that is it. Yeah, so it looks exactly the same. Any questions on that one there? All right, so same thing with this guy, even though it's a ring structure here, your sole purpose of looking is right here at my double bond. And once again, I'm going to redraw it exactly the way it looks. I'm not going to get all cute and fancy and open the ring up or do anything weird like that. I'm just going to redraw it, making my double bond now a single bond. And again, at that point, we were actually adding a hydrogen to each side, again, symmetrical because they're both the same. So truly, you don't even need to actually draw it on this one, but I'll draw it for illustration purposes. Basically a hydrogen to each of those guys. Since it is sort of line structure without the double bond, it adds an extra hydrogen to each side and it would be done. Any question on these symmetrical ones? They're pretty straightforward. Again, double bond, single bond, each guy gets one of the guys that are being added in. Everything else looks exactly the same. Any questions on any of those there? All right, so let's talk a little bit about unsymmetrical additions, which is a little bit different. It actually works very similar, but there is sort of a rule that we typically like to follow when we're doing these unsymmetrical additions. And again, an unsymmetrical addition is when you add something like water, which again, it adds as H and OH, like HBr, HCl. So really like an H and something else being added. The overall sort of reaction that takes place really is the same. So we're just going to make our double bond into a single bond to allow room for it. So if we just drew something like this. In this case, I'll just put a hydrogen here and a hydrogen here. Now, in this particular case, let's just add some water here, and I'll just put water in parentheses underneath. So the exact same thing is going to happen in this particular case, and really our main focus is still going to be right there. And just like the last one, you pretty much can start drawing just like you did before, double bond into a single bond. So let me just recopy it exactly like I see there. I'll just do it kind of underneath again since I ran out a little bit of room there. CH3, CH2. Now I'm just going to make that into a single bond to allow a place for everybody to come in. And we will end up with something that looks like this. Now, what is going to be added is we're going to add the H and the OH, and it's going to work the same way. H is going to go to one and OH is going to go to the other. And in this particular case, there is no difference. You can put the H over here and the OH over here. And this gets us a alkene that now makes a alcohol. So this is really how we can make an alcohol, is basically to add water to an alkene, and we will make an alcohol. In this case, this is a secondary alcohol, yes. And that would be something like 1, 2, 3, 4, 5. That'd be something like 2-pentanol that we just made over here. Be 2-pentanol. Now, when there is a difference, and what I mean by that is when we do unsymmetrical additions, the hydrogen that is added will usually go to the carbon that started with the most hydrogens. So what that means, yeah. This is unsymmetrical we're talking about right now, yeah. So what we're talking about is when we double bond. This carbon right here has one hydrogen, right? This carbon right here has one hydrogen. So there really is no difference. You could put the H on the guy on the left, you can put the H on the guy on the right. But when there is a difference in the carbon-carbon double bond, the carbon that had the most hydrogens to begin with should get the actual hydrogen added to that carbon. So to illustrate that, let me draw one here where we have that situation occurring. Good, yeah. So let's see if I can remember. I'll just do this guy here. Let's do this, I think. That is too many hydrogens. Let's take out a hydrogen before we begin here. There we go. All right, so we got this, and let's do the same thing. Let's add our water as HOH, or just our water. So now when we look at the carbon-carbon double bond, we know we're going to do our same thing. We're going to focus right here. And again, we could still do the exact same thing. We could copy it over. We'll turn our double bond into a single bond. And now we could add our hydrogen and oxygen in one of two ways. We could either add the hydrogen here and the oxygen here, or the alternative to that is, if we redraw it, is to add the guys basically the opposite way, which would be here, to add the H here and the OH here. So there actually is a rule that we follow, which is known as the Markovnikov's rule. That's like a Russian name, I think. And again, his rule is the one we just said there. Basically, the hydrogen should always end up on the carbon that had the most hydrogen to begin with. So when we look at these two carbons, which one had the most hydrogens to begin with? It is this guy, right? He had two hydrogens directly attached to it. This guy has just one hydrogen attached. So really I won't say correct product, but really what is sometimes referred to as the major product, which is usually what you want to draw, it should actually be this way, where the hydrogen that we added on ended up on the carbon that had the most hydrogen to begin with. This is what is sometimes referred to as the minor product. And most of the time you should shoot for the major product. So kind of like what we were talking about with the dehydration, where you have an option of removing the hydrogen and you want to remove it from the one with the least in the dehydration. When you want to put the hydrogen on in a hydration reaction, it goes to the one that had the most hydrogen to begin with. Question on that. Obviously, this is also an alcohol. The difference is actually you get two different alcohols here, right? If you did the major guy, you would end up with 1, 2, 3, 4. That would be 2-butanol, right? And if you drew the minor product, you would end up with 1-butanol, right? Two different alcohols. And again, here our top guy would be really the major product. So in an unsymmetrical addition, the hydrogen always goes to the one that had the most hydrogen in the carbon-carbon double bond to begin with, if there is an option. And that goes for HOH or water, goes for HBr, HCl, H, and something else that you're adding. That is where the H should end up, and the other guy should end up on the opposite guy. Any questions on that there? Easiest for you in a sense, because you kind of have the picture there for you. And again, in all these, we have double bonds. So that is really the center of our focus on all these. And since they all have double bonds, we're pretty much going to do our normal thing, which is super zoom. And then we're going to zoom out. And we're pretty much just going to copy exactly what's there, and knowing that we should always take the double bond and make it into a single bond. So without much thought here, I'm just going to copy exactly what's there, turning my double bond into a single bond here. Now, when we look at this, we see we're adding two things, which would be an addition reaction. In this case, it's an unsymmetrical addition. We're adding H and something else. But in this particular case, it does not matter because each of the carbons in the double bond started with the exact same number of hydrogens. So you could put it whichever way you want. I'll just put the H here and the Cl here. And the reason I say you can put it wherever you want in this case is if you did the opposite, I'll just draw it right here, where you did the Cl there and the H there. Both of these guys are exactly the same. Name this guy. This would be 1, 2, 3, 4, 2-chlorobutane, right? Giving the group the name. You name the guy on the left, it would be 1, 2, 3, 4, 2-chlorobutane. Because you both have the same number of hydrogens, it doesn't matter which one you put it on. Questions on that there. Looking at this one here, even though it's a ring structure, going to do the exact same thing. Going to redraw it, take my double bond out. I'm still going to leave everything else exactly the same. This case, this is water, which means we're adding H and OH. Once again, a unsymmetrical addition. Doesn't make a difference where the hydrogen goes in this case. The answer is it does in this case, because when we look at the original double bond over here, this carbon right here has how many hydrogens? It has 1 hydrogen, as it has 3 lines coming in. This carbon right here has how many hydrogens? Actually has none. It has 4 lines coming in. So the hydrogen should end up on which carbon? Should end up on this carbon, the one with the most to begin with. So in this case, the hydrogen actually should end up here, and the OH should end up down here if you follow that rule. So again, it makes a difference in that case. Obviously, this would be the major product. If you did it opposite, it would be the minor product, and perhaps not so correct, but so you would want to go with this one. Any questions? Obviously, there's another hydrogen here on top. I didn't draw it, so the one I drew is the one we added. Any questions on that one there? Lastly, once again, we're just going to copy what we got going on over here, turning our double bond into a single bond here. Try not to miss anybody here. In this case, we're adding Br2, which is a symmetrical addition since we're adding basically 2 Brs. Yeah. This case, you can't mess up. You're going to put a Br on either one here. And in this case, it doesn't matter the hydrogens because this is a symmetrical addition. Everybody's getting the same element basically. So you can put it on either one. Any questions on any of those there? In this case, question on addition reactions. Again, really only the unsymmetrical one you just got to kind of watch out for. Again, hydrogen to the one that started with the most. Hopefully you can see a pattern that nothing really changes except for one very small part of the molecule. And that's where you should focus in on these reactions and all reactions is which part changes and how it changes. Again, up on Canvas, I put like an organic reaction sheet where I just tried it in words, tell you like, hey, make it into a double bond, into a single bond, put this guy here and this guy there. And if you just sort of think about and figure out the general way these things occur, they really do occur the same way. So this is the hydrogenation reaction that we just talked about, which again is symmetrical. And again, here, since we're adding hydrogen, we can't really mess it up. And we see what we've been talking about. Again, double bond into a single. And everybody gets a hydrogen in this particular case. Again, anything on top of the arrow, really not going to participate or do anything in the product side. So don't put any of those guys on the product side. Not much is going to happen other than they're there to speed up the reaction. All right, so why don't you try this one here, which is 1-butene using a platinum catalyst. Okay, so butene is 4 carbons. 1-butene means we got a double bond happening there at carbon number 1, and then obviously our hydrogens there to complete it. And for this here, I'm just going to draw out the hydrogens on this guy just so we can see. Obviously, that is where everything's going to sort of happen. Now that we have our structure, once again, we're going to just focus in on our double bond here. And again, turn it into a single bond. And in this case, since we're adding hydrogen, we're just going to give each of those carbons now a hydrogen. And we would put a hydrogen there and a hydrogen there. And there we go. Yeah. Any questions on that one there? Yeah. Yeah. It doesn't do anything. It's just on the arrow. It just speeds up the reaction. So it's not really involved in the product. So typically if it's a catalyst, you won't get incorporated into it because a catalyst is really not a reactant. It's not a product. It's just there really to kind of speed up the reaction, make it occur a lot faster. Yeah. Why does the guy at the end or? Yeah. So again, that's one, the hydrogens got added in there, but carbon does need 4 bonds, so that's where the hydrogen would end up to get 4 bonds. Other questions? So as I mentioned, adding this will turn kind of oils into margarine a little bit more solid at room temperature. We'll talk about it when we talk about fatty acids later on, but these double bonds doesn't allow all the carbons to sit really nicely with each other. A lot of kinks in the chain, and they typically will become more like oil or liquids at room temperature. By getting rid of those double bonds, allows all the carbon parts to sit really nicely together, makes it a little bit more solid. As we'll talk about when we talk about fats, basically, fat in like steaks, they're all single bonded. They sit really nice and you get, sort of a hard fat. I'm going to skip these as they're very similar to what we just did. Obviously, in each of these cases, we would take the double bond, make it a single bond, and add a hydrogen to each of these spots. So really, this guy would end up looking like that. And this guy would end up looking like this, adding in the hydrogens. Any question on addition reactions? Okay, so to finish up here, let's talk about then benzene and benzene sort of rings and some of the historical sort of names that go with benzene rings in this particular case. So let's do that. And the hydration reaction, obviously, we talked about as well. So I'll skip that. Let's talk about aromatic compounds. So if something's an aromatic compound, it has that benzene ring. And as we alluded to before, benzene looks like that. It's basically a 6-member ring that has 3 double bonds in it. You could also draw the double bonds on the other side. And a lot of times in like your type of book, they will actually just sometimes just draw like a little circle there in the middle. And that's because those double bond electrons, they are what are referred to as being delocalized, which means they're just moving around. So at any given point, the double bonds maybe look like the guy on the left on the top, or they may be over there on the right. So sometimes the people will just kind of draw like a little circle in the middle to indicate that is there. So when you do see the circle, it does represent one of these 2 structures that has, again, the 3 double bonds in it. But it's common, especially in your book, to kind of do that. That means that there will be 1 hydrogen at each of those carbons, which is represented here as well. Now, benzene's aromatic compound. And again, these are the 3 or multiple ways that you can see it there on the bottom. They are planar. They have basically the carbon has 4 electron pairs and 4 bonds, so sort of a tetrahedral, but it's almost very planar the way the ring comes together. Like all those guys are within the same plane of the molecule. And again, those electrons are basically moving around. So when we have a benzene ring as part of the main, or when you have a benzene ring there, it typically is the main part of the compound. Not 100% of the time, but most of the time it is. And to name these, there are some sort of historical common names that are still used today. And these are some of them. We saw phenol when we talked about the alcohol. And that, again, basically is a benzene ring that has an OH group on it. Aniline is a benzene ring that has an NH2 group on it. That's what is known as being an amine, basically. And benzene that has a methyl group, which could be drawn one of two ways, is known as toluene. So sometimes people will use these names very commonly, especially toluene, aniline, and phenol. They're used very commonly. Without it, people will sometimes call it methyl benzene. But most people will still use sort of that historical name. So you should be very familiar with sort of these three, I would say. They do pop up a lot, that sort of common name or historical name that's used a lot. So a benzene ring with a methyl group is toluene. Benzene ring with an NH2 group on it is what is known as aniline. And a benzene ring with an OH group on it is known as phenol. Once again, if you do have one of these guys on there, we don't do any numbering of where that particular group is. For example, the methyl group, because it's kind of part of the whole name. But if that carbon would be carbon number 1. So if there are other things attached, that would be carbon number 1. That would be carbon number 1. And right there would be carbon number 1, obviously, for that guy. But again, we don't incorporate the number into these sort of common names. Now, if we do have some other groups besides those guys, we just would put benzene at the end and name the groups. So if you have just one group attached, that is chlorobenzene. Again, there's no need to give a number because pretty much wherever you drew the chlorine would be carbon number 1 in this case. But when you do start to get 2 groups attached, you do need to give numbers in this case. And this would be 1, 2. They're both chlorine, so it don't matter where you start. By the way, it also will follow the rule we talked about of you got to number through the double bond, if you remember. So because there's 3 double bonds, you can pretty much go any way you want in a benzene ring, clockwise or counterclockwise. They both will work because pretty much by those 3 double bonds, you've got to go through a bond no matter which way you sort of go in most cases, unless you kind of go, this way. Here would be one exception. But so this would be 1,2-dichlorobenzene. This would be 1,3-dichlorobenzene, and this would be 1,4-dichlorobenzene. These guys also have sort of a historical way where we do not use numbering. The 1,2 positioning is what is sometimes referred to as the ortho positioning, and this is sometimes referred to as ortho-dichlorobenzene. The 1,3 positioning is known as the meta positioning, which is sometimes abbreviated with just an M. So that would sometimes be called M-dichloromethane. And the 1,4 positioning is what is referred to as the para positioning, or para, or P-dichlorobenzene. So these are 3 historical names, are ways of naming something without numbers that you should be familiar with. So ortho 1 and 2, meta 1 and 3, and para 1 and 4. So those are common positioning ones. And again, so if you see a name where there's just like an M in front of it with a benzene ring, that is telling you the positioning of those groups. There are 1 and 3 on the ring. If you see an O, obviously 1 and 2, and a 1 and 4 would have a P sometimes. And again, so a lot of times they won't write out meta, para, and ortho. They'll just use O, M, and P kind of in the name without the numbers. So that kind of takes place of the numbers. This only occurs on a benzene ring. So you got to have a benzene ring for that to sort of occur. Any questions on that there? All right. Now, if we did have multiple groups attached, we obviously would want to go whichever way gives the groups obviously the smaller number, and we would name in alphabetical order. So looking at these guys here, we have some of our historical parts to these guys. This guy right here is the aniline part. And again, although we don't give the number, that is going to be carbon number 1, carbon number 2, and carbon number 3, where we get the bromine. This part right here is the phenol group. And again, using the OH as carbon number 1, we're going to go carbon number 2 counterclockwise, 3 and 4. Again, if we went clockwise, we would have 2, 3, 4, 5, and 6. So again, give us bigger numbers if we went the opposite way. So everything in organic is lowest numbers. So we want to go, in this case, counterclockwise. But just like we talked about before, alphabetical. So even though the bromine has a larger number, it does come first in the name. So that is 4-bromol 2-chlorophenol. And lastly here, this is toluene right here. And in this case, we actually have 3 groups attached, 2 bromines, which is our dibromal, and 1 chlorine, which is our chloral. Again, in this case, it looks like actually either way, I think we'll give you the same numbers, but they went clockwise here. It gives us a 2 and a 6 for the dibromal, and our chlorine ends up at carbon number 4 in this case. So these again could look really intimidating, but you just got to put a box over those sort of historical kind of names, and then you kind of number everybody accordingly. Wherever that historical group is attached, if you will, that again is always going to be carbon number 1 in each of these things. So if we look at this guy here, this is a benzene ring with a chlorine. And since it's the only group attached, this should be chlorobenzene. Again, this is not cyclohexane because there's 3 double bonds. And this is not 1-chlorobenzene because you do not need the number. Here, we would have a methyl group and a methyl group here. And that would be 2 methyl groups. And if we did carbon 1, carbon 2, carbon 3 clockwise, that would be 1,3-dimethylbenzene in this case. You could maybe use toluene as for one of the CH3s if you wanted to, but this would be more the historical name. Any questions on benzene rings? Okay, thank you for listening. I believe